Let's see what we'll be doing today. Okay, so the main focus is to build a 4-bit parallel adder subtractor unit. Okay, that you may have already covered. You should have already covered in unit 3 or 2. So this is the final thing. We are looking forward to make it in Proteus. Also, while making it, we'll be seeing these things, 4-bit full adder IC, okay, 7483, the pin diagrams, and then we'll be building our 8-bit parallel adder. We'll try cascading to 4-bit ICs and do a 8-bit operation, addition operation. Next, we'll use a XOR gate. Okay, in hardware lab, we'll be using IC 7486. But for Proteus simulation, I think the IC is only available as pin diagram, schematic diagram, but not as this, uh, like not as the simulation. Okay, so this is the logic symbol thing that we'll be using for simulation. Okay, so this is in brief what we'll be covering today. Excuse me. Okay, so let's start. This is the pin diagram of IC 7483. Okay, so 7483. In 7483, we have 4 interconnected full adders. You can see, right, this PPT? Yeah. So within this circuit, basically there will be 4 interconnected full adders. And you can see there are pins like A4, A3, A4, A2, sorry, A1 is here, A2 is here, pin number 8, A3 is pin number 3, and A4 is pin 1. So these 4 inputs, it is shown in this table, these 4 inputs forms the first 4-digit binary number that will be adding. And next, these B inputs, B1, B2, B3, and B4. So this is the second 4-digit binary, right? So these are the 2 inputs that will be added and we will get a 4-bit sum. So the pin numbers for this sum bits are 9, 6, 2, and 15. Okay. When we'll be doing in Proteus, that will be more clear. No need to worry now. Okay. Now this C0 is the carry input from previous stage if present. This is the basically carry input C0, 0, right? So for 4-bit operation, if we are doing addition, then C0 is kept 0. And then this is the C4, this is the carry out, this pin number 4. So this is briefly the pin diagram of IC 748. Now say, where did I get all this information? Okay, so whenever say you have an IC like this IC 748, you may not know what are the pin details and how that particular IC functions. And for that, you need to get a data sheet basically. Hold on, let me show you. I have downloaded. Okay, you can see this is one particular instance of 7483 IC. Okay, so this is manufactured by Fairchild Semiconductor. So this particular manufacturer will publish also a data sheet that is available. Many such data sheets are available in internet that you have to see, and from there you will have to look for what are the specific pins and the labels. Okay, so this is very much implementation specific. Just think like that. But yeah, this is more general that in this case, 7483 at least will get the same pin organization for most of the standard manufacturers. Now they have also given a truth table. So you can see that if this A1, A2, A3, A4 output, and sorry, A1, A2, A3 input, and B1, B2 input. This is like this 2-bit addition. Then what will be the sum and what will be the carry? And this is the logic diagram. You won't understand, and I'm not going to explain this. This is a bit like out of scope. All right. So this is pretty much I wanted to show you. Anyway, next, let's look at how we are going to make a circuit with this. So before that, let's just see. This is a recap. You may just recognize the circuit. Very simple. So this A0, A1, A2, AN this is an n-bit parallel ladder. Okay. So how parallel ladder works? So any parallel ladder can add two n-bit numbers, binary numbers, parallelly. Okay. That means at the same time. You see, if I consider this diagram as a 4-bit parallel ladder, there are 4 full adders, basically, one by one. So 4 full adders will add, starting from the lower bit, is 3 bits at a time. One is carry input and 2 input bits. So in this way, 4 full adders are able to calculate sum of 4 digits of the 2 inputs at the same time, right? So this is the truth table. This you may refer, this you may write in a copy, because that will be needed when we make the circuit. That will be needed to verify. Okay. This is the first experiment. We'll just see how this 7483 IC works. Okay. It should work as per the pin diagram just showed and the truth table. Okay, let's make it in Proteus now. Okay. Do you all have Proteus installed, or you're using some other platform? Are you using Proteus or some other platform?
Ma'am, Proteus as well as Topic for Sports.
Proteus. Proteus, right? Okay. Thank you, Avik. Okay, let me tell you one thing about Proteus. If anybody is, excuse me, if anybody is facing any problem with Proteus, like opening it or anything, uh, you have to always install all the dependencies that it needs. Any additional framework, it may be, I don't remember exactly, it may be some .NET framework or Visual C++ framework that is additionally needed for installation. And then when you're opening it, say from run from here, so you have to right click on it and run as administrator. Don't forget to do this, because if you are not doing this, you will not be able to access the libraries. Okay. Okay, let's just start from scratch. Okay, this is what I had built for myself. So let's just start from scratch. Okay, I'll be recording this meeting because we need to record the meeting and maybe share with you later. Okay, I forgot to start that. So Okay, so this is Proteus. Now we are going to add components. So this is the peak parts tool. Let's go to the search and check for. I'll just simply search 7483. Okay, and
This call
whenever
is
we
now
are
being
choosing
recorded.
components, we need to always see that this particular component is also available for simulation or not. Because whenever Proteus performs a simulation in the background, it will execute some script. So sometimes this libraries, this components does not come with a script. So you will then won't be able to uh, perform a simulation like that. Okay, so I already experimented, and anyway, this is the component. You may take a note of it. Okay, just choose this 74 LS83 component in Proteus. Okay, this with this you will be able to simulate. All right. Next, what else we need? We may need a LED to show the output. Try red LED. Okay. Again, I have to get a active component which can be animated. Okay. I've added it. Okay. Let's now. Okay. Now let's see. You can see it. Is this good enough? Large enough? Yeah. Okay. Thank you. Okay. Okay. Thank you. So you can see, right? These are the two inputs. A1, A2, A3, A4 is this four binary digits for the first input, and this B1, B2, B3, B4 is the second binary number, and then this is the sum, and this is the carry. Okay, carry out. And this is C0 is the carry in. So it matches exactly with the data sheet, right? All the you can just verify yourself. You can get the data sheet in the internet. Okay. All right. So I'll just go to the next step. What I'll do, okay, just do me, give me two binary numbers, okay, just in the chat box. What you want, what you would like to add, put in the chat box. Two numbers we want to add. 1011, one number I've got, that is for A. Okay, let me write 1011. Then, okay, which one should, that's enough. Um, Another I'm taking 1001. Okay. Okay. So let's just make the circuit in this way. So for one, we put a 5 volt VCC. Okay, from power. I just write power. And for zero, I give ground. Okay, put it to ground. So let's make it this way. So we have, let's just specify the bit positions. This is 4, 3, no, this is started from 1. Okay. 4, 3, okay, this is say the bit position. This is a, I hope you understood what I mean. All right. So let's just see A0, sorry, A1, A2, and A4. These three bits are added to power supply. Okay. So let's just get this from here. This is the terminal. I'll be using terminals, and there is this power thing. And let me take this. symbol like this.
Ma'am,
Yes, yes,
ma'am, the IC number was 7483, but
yes.
when we are using it in Proteus, we are using 74LS83. And so why that LS part?
That is actually due to the IC packaging and everything. Okay, that is uh, related to how an IC is packaged, which technology, semiconductor technology, and everything is used. So if you look at the data sheet and all the specifications you'll get, okay, so 7483 is the number. So this LS may change depending on the implementation and everything. Okay, are you getting me? So that is actually specific to this implementation technology. Okay. So we are not concerned about ALS or how it is actually implemented. Rather, we are more concerned about the functionality, how it works. Okay. So yeah, let's see where we were. A1, A2, and A4. So let's add them slowly. A1, A2, and A4. Okay, correct, right? Next, B. Okay, B1 is connected to power and B4 is connected to power. Let's do that. B1 is connected to power, B4 is connected to power, right? Now we'll put C0 as ground and all these inputs that is 0 to ground as well. So let's take a ground, the ground here. Okay. You have to add all this, okay, all the terminals ports should be added to the web, otherwise the input will be like unknown. So you will not get correct result. I'll show you one such case where you may get wrong result due to this wrong circuit. Okay. Okay. Now some bits should be applied to some LEDs so that we can check how the LEDs are glowing, and by that we can understand some bits. Okay. Which are one, which are zero. Let's go back to components, and this is the red LED. We put it here, one, and let's rotate it a bit. Okay, looks good. Okay, I'll just copy it and paste 4 times. One, and okay, let's connect it. This is the 4 things I need to connect the carry as well. Okay, now what to do with this post? They will be obviously connected to power. I take another ground, put it somewhere here, add them. Okay. So this is pretty much the circuit, right? So we saw the numbers were already put like how it should be. The inputs are given, and let's see. Okay, can someone quickly calculate what is the sum we are expecting? I'm also calculating. So please calculate as well and put it in the chat box.
Ma'am, what is the TOS 4321?
Which one?
That you written, ma'am.
Oh, okay. So these are basically what I meant. That is the bit positions. Okay, like here we are using it 1, 2, 3, 4. So like that, this is what I have written. Okay, so this is the input. So to understand which one is the first bit, second bit, third bit, and fourth bit, I have written it. Okay, this is no significant. This is for just my understanding that which bit position is like I'm handling. Okay.
Okay.
Shuchira ma'am, I like to
Yes.
say one point
Yes.
that actually, if the college reopens and they need to do the hardware lab, in
Yes.
our hardware lab actually, mm, if it reopens, then only it is going to happen. Actually, we are using mainly the CMOS ICs, okay, and that is starting with 4000 series. So another IC number they may note. The way they are doing fine, they may note another IC number. I am writing in chat box, that is IC 4008, and from the nomenclature itself, they can understand that it is a 4000 series CMOS IC, okay. And in lab, actually, this IC is available, okay. So if the hardware lab reopens, then they might have to use this IC number. So they may note it down, okay.
Yes.
That's it. Okay.
Thank you, ma'am. Yeah. So as I said, that there is no need to really worry about how this IC is implemented, or even if you don't know what is exactly the pin diagram and everything, you can always look for this particular IC in the internet. Just do a Google search. You can download the data sheet from any manufacturer and you can see. Or we may, as in the lab, we may have the manufacturer name as well. So we can always have the data sheet from internet, and then we can see what are the pin numbers and what those pins are meant for, right? And how
that is similar to this same this
LS,
yes, the same thing. Yeah.
Yeah.
Only certain bit position will be changed.
Changed.
It's
okay. Right. Thank you, ma'am. Okay. So have you calculated the sum? Just write it on the chat box. This is very simple. I think I have calculated, but we need to see that I could add or not. Am I correct? I think one bit is wrong. Yes, thank you. Right, I did a mistake, right? Yes, you should always catch that. Okay, I may make mistake. So let's play this, okay? This is the play button. We'll move it. Yeah. So is it the correct input? Say yes loudly if you agree. You understood? The output 10100. So the bit position zero. The bit position for S1 is 0. Right? We from more significant to low significant bit. If I like read out, it will be like 10100. Correct? 1 voltage, see, you can also see this square, right? Red square. This always means high voltage. High, the line is high. That's why the LED is glowing. And whenever the line is blue, like this, that means the line is low. So there is no voltage. So the LED is off. Correct. So in this way also you can see that it is 1. This is low bit position. So 0, 1, 0, 0. This is absolutely matches with what we got, right, by the sound. 1, 0, 1, 0. Correct? Okay. So end of discussion for 4-bit parallel ladder. Now, if you have any question on how a parallel ladder works or whatever I did, if it was not meaningful to you, even a single person should come forward and tell me that so that I can understand and I can repeat. Okay? I'll wait 2 minutes, perhaps. Please confirm that you understood, or is there any confusion?
Ma'am, input part, how you have connected? Explain once more, ma'am.
Okay, thank you, Sandeep. Let's try again. Okay, Sandeep, I'll ask you. You only tell me, okay? That will be better.
Okay, ma'am.
Okay, so let's just focus. You understood, right? A and B are 2 inputs, right? 2 inputs.
Yes, ma'am.
Exactly. So, if I have to say in a circuit, I am preparing a circuit. Okay. So in a circuit, what voltage we are gonna put in this bit position? In the say this bit position. The
Ma'am,
lowest
that will.
yeah. Tell me.
Ma'am, one is there. That means high voltage. I think so.
Yes. Yes. Correct. Yes. Correct. Yeah, be confident. You are absolutely correct. And
Okay.
1 is high and
0 is low.
this is low. Correct.
Yes,
So
ma'am.
if I so we know in the pin diagram, you see in the pin diagram, let me size is again. Yeah, so you can see, right? So
Yes,
in the
ma'am.
pin diagram, A4 is the MSB, most significant bit. Okay?
Okay.
And A1
Okay.
is the LSB. So if you are reading from MSB to LSB, so how you'll read? Tell me, just read the number 1, 0, 1, 1. Correct?
Yes, ma'am.
Yes. Now
Yes,
you
ma'am.
see how I have connected. Look at this. A4 is 1, right? And
Yes,
this
ma'am.
is my power. This is my power. This triangle.
Okay.
Above. Okay. So this line is connected to, just look at this dot. Okay. This line is connected to high power. Correct?
Yes, ma'am.
Any confusion? Your voice sounds like not
No,
convinced.
no, ma'am. No, it is clear.
That is clear, right?
Yeah, completely clear.
Okay, thank you. Then A2 is also connected to high power. A1 is also connected to high power. You got the ones. Now A3 has to be low, so it is connected to the ground. You see the line coming from the ground straight up here, right? So
Yes,
from this is connecting to 3, pin number 3. That is
yes,
it.
ma'am.
So this is how one connection is made. Now, if you have Proteus, you should try it yourself. You will always get correct answer. No need to like draw in this particular way only. I mean, the way I have connected. Just keep in mind what logic you just said to me. 1 is high, it should go to the power, and low is ground. Okay?
Oh,
So just
okay.
make the wire connections similar according.
Okay.
Okay? So once you make the connections, and for LED, you see this position you note, please. Okay? This cathode anode position. So this anode position, this S1 should go to the positive, this plus side of the LED, and the other side, this you can see this vertical line, right?
Yes.
So this
Yes, ma'am.
position should be always ground. Okay. So when we make a circuit in like physically on the breadboard, sometimes there will be some resistor here. Okay, some resistance will be there, like 10 k or something. But this is more of a logical diagram, so I have not put the resistors that will simply like increase the complexity of the circuit, but we may have to put some resistance wherever needed, not the ground side, but where I am applying voltage. We may need that sometimes. Okay, so that you remember, you draw the LED logical diagram. You will see that the vertical line that should go for ground and the other side should go for the high voltage. Okay.
Okay, ma'am.
I mean the voltage. Yeah. So
Okay. Thank you.
yeah,
Thank you,
welcome.
ma'am.
Yeah. All right. I think this is clear.
Now, one question to all the students: if I want to change the input pattern, instead of giving power and connecting to zero, so how can we give variable input?
Ma'am, with that logic probe and logic status.
Yes, that is so. Actually, for A, you can give four logic state. That is, the logic state will be there, and for B, we can use another four logic states. So you can give variable input, and this is for the static input, right?
Yes, ma'am.
So I think for all the, suppose if you have a truth table of, I have shown you in the theory class, one truth table may have some 4 plus 4, 8 plus 8, maybe 12 plus 12. So certain particular values of A and B. So you can make the truth table by using the variable input also. Okay, or if in the lab question, in particular this type of question is there that the A and B values are specified, then you have to connect it like that. And if some generalized circuit is there, then you have to change accordingly. Okay.
Yes, ma'am.
Okay. Okay.
Thank you, ma'am.
Madam, can I share the attendance link?
Yes, yes, sure, sure.
Okay.
Similarly, we can use logic probe as well in
Yes.
place of direct ground.
Yes, you can just see the output in red and blue. Red is generally the the as if the LED is glowing, and blue
Yes,
is the LED is off.
Oh, okay.
Either I have not shown the LED part previously, but what ma'am told, the connected to positive and negative. If you remember in the previous class, I have shown you one example with the ground and how to connect with the power. You can right click and go to the terminal, and you can select the power and ground from there also. Okay. So I'm sharing the attendance link in the chat box. Okay.
Ma'am, in the hardware lab, we will doing the experiment like this only. Means we will be connecting some LEDs and grounding
Yes,
and
yes,
powering.
yes.
Okay.
We have to connect some LEDs and we have to identify which portion of the LEDs. And you know that if you have a LED, so there are two legs. You can say one is the longer leg, another is the shorter leg. In the basic electronics lab, you have done,
Longer
right?
is positive.
Yes, longer is positive and shorter is the negative. So you have to connect accordingly to the power, and you have to put it in the breadboard accordingly. Okay. So
Okay.
if it happens, then we have to practice a little bit. Okay.
Ma'am, what is the required voltage for this IC?
Which one? This
The
one. Voltage is we always give plus 5 volt, and in the lab we have either 0 or plus 5, like that. Okay, the kits we are having, digital trainer kits, we are having plus 5 volt and 0. Majority of the ICs, some of the ICs they are using plus 9 volts, but still majority of ICs which are we are having in our COA lab, and COA and digital lab is common. Okay. In the same lab, we actually do digital lab and COA lab, hardware lab. So we use 5 volt there.
then the output which we are getting at the term, those LEDs are also getting 5 volts, or they have inbuilt resistors to.
No, they are actually, there are certain threshold value. If you think of 0 as the ground and 5 as the peak, so actually the LED, how much current through the LED it will pass depends on, you have the normal current calculation, right? V by R equal to I, right? So actually we should have put some resistance, but we do not used to put the resistance because if you actually, if the current value is too much high, the LED could have been damaged. Okay, but as it is 5 volt and it is not too much of high current flowing through the LED, so we do not put resistances like ma'am said 1K or maybe 10K through this circuit part. That is ma'am told you, right? So between the LED and ground, we should have used some resistor in between, but in practical without doing also we have actually obtained the output. Sunil, have you got the idea?
Yes, ma'am.
Yeah, okay. Okay, Shuchira madam, you can continue. Okay.
Okay, thank you, ma'am. Okay, so there are few confusions. So let's see. Rimpi, so you made some query. Can you just tell me once again, like unmute yourself and just tell it to everyone once?
Hello, ma'am.
Yes.
Ma'am, I didn't understand the C4. Matlab, what is it? What is happening there?
Okay. So you want to understand
Output is coming from the 4. Then what is the use of C4?
okay, let's not think like that. Let's just make it a bit easy. Okay. Let's just so what is the carry in this sum? Tell me. What is the carry in this sum?
Ma'am, sum is okay.
No, just tell me. No, I'm going to answer you. Just tell me. 1, right? That is the carry, right?
Yes, ma'am.
So
Yes, ma'am.
here we have in sum 4 bits, and this carry, you must say that that is the 5th bit, right? In the output, that is the fifth bit, right? So, but what we see in this particular pin diagram, you have to see how the IC is basically designed. Okay, so they have numbered it like 1, 2, 3, 4 for 4 sum bits. Okay, for these 4 sum bits, they have numbered like 1, 2, 3, 4, and then the carry bit, they have named it C4. So this is a design thing that they have named it C4. They did not name as S5, or they did not name as C1.
Ma'am,
But
why have you
that
given?
is the choice. Yeah. Tell me.
Why have you given that C0 low voltage?
Yeah, C0. Why it is given low voltage, right? What is C0, by the way, here in this sum? Cannot see, right? I'm sure that you cannot see that because I have not written that. C0 is the carry input from previous step. Let's go to the diagram once. You can see this one, this particular C in thing.
Yes, ma'am.
Yeah. So this is C0. Okay.
Okay.
Okay, I think. Hold on. Let's just consider this 2-bit adder. 2-bit full adder. Okay, forget about rest of it. So you have got this C in and in this case, this is the lowest order, right? A0, B0. So there is nothing else in the right hand side. No more bits are being added. No, obviously there will be no carry. So we set this C in as 0. Okay.
Oh, because of the carry.
Yeah, that first carry C0. So this is C0.
Okay. Means that there is no carry for the C0.
Addition.
Then we
Exactly.
will take. Now I understand.
Yeah. Right. Let's. Okay. What else? Any other confusion? So everything is clear, or there is any more questions? Okay.
Ma'am, in this circuit, why have we used ground on the opposite, on the output side as well, where the red LEDs are?
Opposite side means you mean which side?
Ma'am, output side, why have we shorted the red LEDs with the ground?
Yeah, this is not actually short. This is by this you have the breadboard. Just imagine a breadboard. So there will be places will be connecting it to the ground, right? There will be like points. So this is like if you imagine it as a real wire, it will go to the ground. As simple as that. As that. So there is nothing like I'm not doing a connection. That means if I just remove this wire, if I remove this wire, this won't work. Any
Okay,
see
ma'am.
LED is a diode, right? So diode needs to have this one is anode side, one is cathode side. So both side needs to be connected basically to complete a circuit. Just circuit means obviously say it will have both the ends connected. Otherwise the circuit won't work properly.
Okay.
Right? The positive end and the negative both should complete. Just think, look at the town circuit. Circuit, if you imagine, it's like a circle. So it will always complete. Only then it will work. So if I am not giving this ground, then this LED won't even light up.
Yes.
Circuit will not be closed. Rather, if you
Yes,
have
yes.
some bits, you need to close the circuit, right? You have one battery negative to battery positive, then you have some resistor, then you have the positive terminal of the diode, then the negative terminal of the diode should be connected to the ground. Then the full circuit is simple circuit. One battery, one resistor, one diode. How will you connect? You connect the battery negative, smaller side, then larger side positive, then the positive side of the battery is connected to the simple resistor, then and the last end of the resistor is connected to the cathode of this LED, and this the negative part is will be, that is the positive terminal of the LED, and then the negative terminal of the LED will be connected to the ground. So simple circuit. So here the LED, other terminal of the LED cannot be put like, we cannot keep it like that way, right? So it should be connected to the ground.
Okay, ma'am. Thank you.
So any more questions, or we can move forward? I think everything is clear, right? Just give me a confirmation from your side. So I'll move to the next experiment. Okay. Okay, thank you. Okay, no need to. Okay, I'm just moving forward. So let's look at the next experiment. The next experiment, we do the same thing. Okay, we have already got a 4-bit adder, right? Now we are going to cascade another IC, another 4-bit parallel adder. to get a 8-bit sum, 8-bit adder. Okay, so this circuit, you can see the diagram, right? Just you can sketch it on your copy and just reflect a bit. You can see that you see this x0, x1, x2, x3, and then x4, x5, x6, and 7. This forms the first input, first 8-bit number, and this y, y0, y1, y2, y3, then 4, 5, 6, 7. These y's are forming the second 8-bit banana. So we'll be adding this 8-bit x with the 8-bit y, and we'll get a 8-bit sum. Okay, just the previous experiment a bit extended. That's it. How we are going to extend that? This is a simple connection. Just this point. I'm marking it. Okay. Just please note it down or get the image from somewhere for your reference. I'm just annotating it here. Just focus on this part. What is happening? Say this is the first adder. Say this is the circuit we have already made. This adder we are working with. Now we saw this C4, right? I cannot write better than this. Anyway, you can understand, I hope. This is C4. This is the carry output from first 4-bit addition. That we will forward it, we'll connect it to C0. C in is C0. C in is C0. So we'll connect it to C0 to the other 748. So we have to add this part, this part. This circuit we have not done yet. We can simply copy and paste anyway. But we need to make sure this is the connection made from C4 of the first IC to the C input of the second IC to get the this is the 8-bit sum, and the carry output will emerge from the C4 of the second IC that will be added. Okay. So what is happening, you see, this is the diagram, right? If you are wondering that why we are adding this C out and C in and how this is actually working, just reflect on what you have already studied. This particular diagram, block diagram, right? This is a functional block diagram, how it works. See, in each of the 2-bit full adders, in each of these 2-bit full adders, the carry out from this 2-bit sum, this 1-bit operand. So this is 1-bit output, carry output, that will go to the next full adder, and again it will operate on these 3 bits. This C in will be some 0 or 1, whatever, coming from previous stage. And in this way, stage by stage, the carry will flow and emerge from the last adder. The highest bit position that is being added by the highest position or highest stage full adder, from there we'll get the final carry out. And from each stage, bit position wise, we are getting the sum bits. You already know, right? This is also known as this ripple carry adder. This carry is rippling through different stages. So just extend it in your mind. This 4-bit full adder, this is a 4. Just imagine it is a 4-bit full adder instead of a 2-bit adder, and you are connecting it to another stage that is also 4-bit. So we have like 2 stages, and then from one stage the carry output should go to the input of another to the next higher stage. Okay. This is the first lower order stage. This is the higher order stage, and the carry is again rippling through the circuit to the next stage. and emerging the final carry output from the last. And from each stage, we are getting the sum. Right? So we can proceed to implement this, right? And ending the show and keeping the annotation. We'll do this, stop the simulation. Okay. So let's just see. This is something I can copy later. So this is your lower order stage, say, and this is your higher order stage. Okay, we suppose suppose that we'll do make the circuit in that way. Okay, and let's just put the LEDs also, because that is not much problematic. That is the same thing. Right. So let's just add them. You see how I am connecting. You are going to click once on the terminal and then just leave it here and click another time. That's it. No much hassle here. You can drag and shift them. Okay. Let's just get another LED for carry. Is it somewhere around here? Here you go. Now all will go to the negative sides are going to the ground. Have to connect each of them. Okay. So this part is complete. Okay, now give me an 8-bit number. Okay, we'll make this static circuit only like we're doing. Okay, give me two 8-bit numbers and their sum. Okay, we'll see. We'll verify it with the circuit. Okay, quickly. There are more interesting things to come. So let's just do it quickly. Type in quickly. Am I not audible?
Yes, audible.
Yeah. Thank you. Yeah, please give the inputs. I want to take the input from your side. Okay. Thank you, Anika. So let's just try this. I'm keeping this and let's try this sum. This is A and this is B. So I'm doing the sum, you also do, okay? We need to cross verify that I have correctly calculated or not. 1, 1, 1, 0, 1. Yep. 1, 1, 1, 0, 1, 1, 1, 0, 1. Okay. So I hope this is the result you got, right? 1, 1, 0, 1, 1, 0, 0. 1, 1, 0, 0, 1, 1, 0, 1. Got this sum? 1, 1, 1, 0, 1, 0.
Yes, ma'am.
Right? These are set. Right. So I'm correct. You are correct. So this is. Let's see the circuit. What the circuit tells us. Okay. Let's first give the inputs. Okay. So this is like we have to see. I'm writing the bit positions. Don't get confused. So I'll write from 8. 7, 6, 4, 3, 2, 1. Next 5, 3, 4, 3, 2, 1. So let's see which are the lines that should be high. That would be A1, 1, 3, 4. Let's just do that. 1, 3, 4 in the first. Okay, so we considered this U1, level U1, this circuit is the lower stage. So this is 1, this is already high, and this should go low. 1, this should 1, 3, 1, 3, 4. Okay, that was already high. Okay, let's just connect. 1 is high, 3, 4. We have got 1, 3, 4 connected to the power, and this one bit, this second bit is ground. The second bit should go to ground. Okay. Let's complete this B part as well here. B2 and B4 is high. So let's see. So B4 you can see is already connected to the high power, and B2 I'm connecting to high. So it got B2 and B4 is high, and both are the other two bits are low. B1 should go to ground, and this one ground. We have completed the lower order 4 bits. Now let's look at the higher order 4 bits. And for this, I'm taking a separate power line because just for our simplicity only. We don't need two BCC lines really. We can connect to the previous ones, but just for the sake of clarity of this diagram. Okay. So let's see what are the higher bits. Only this will go as 1, 2, 3, 4. So third and fourth is connected to high. So only third this one, the B part second and fourth. Second and this one. Second and okay, and rest of the bits should go here. Okay, all the rest of the bits to 0. I hope it is clear. And let's just see if we get what we calculated. Okay, let's see. Let me save it. All right. So let us read it. Let's just read the glowing LEDs as one. So I'm reading out, you verify, okay? So from higher order bits, it should be 1 0 1 1 0 1 0 1 1 1. Something is wrong. 1 0 1 1 0. Something is wrong.
Ma'am, connection is wrong in higher order. Ma'am, it would be 1011. You have given 1010.
Okay. Which side? This. Okay. Can you point out once again? I didn't get which one. Let me see. I have made some mistake. 1100 1101.
Ma'am, look, B4 is 1, B3 is 0, B2 is 1, and B1 is will be also 1.
Okay. Let me see. Okay. Here. Here. This one. Let me stop the simulation. See what is happening. Go 1010.
ক্যাশ অন ডেলিভারি আনঅ্যাভেলেবল কোভিডের জন্য
1 0
ক্যাশ অন ডেলিভারি আনঅ্যাভেলেবল কোভিডের জন্য
1010. Okay. And then 1 0 in the upper side. 1010. Equals 1 0 Okay, maybe. Think. Okay, sorry. I did not do anything. There is a mistake. Okay. So you did not tell me the most important mistake I made. I figured out.
কোভিড ছিল
Ma'am, there was a carry part.
Yes, exactly. That is the thing I explained in theory. I made the circuit wrong. You see. Okay, thank you very much. That is the that is the thing. So what happened? 4 bits got calculated. The summations got calculated separately, right? So it did not happen. This cascading thing I did not. So what I have to do? I have to delete this. This is what happens when I try to do something shortcut. Okay. So C4 will go here. And then I don't need this LED, right? I'm removing it. Okay, everything else is good. Looks good. C4 is cascaded to C0, right? And everything else is good. So let's just try again. Okay, now 1 0 1 1 1 0 1 1 1. Is that the result? Yes, 1 0 1 1 1 0 1 1 1. Correct? Yes. Convinced everyone? See, I missed the cascading part. And in that case, what was happening? Two sums were being calculated separately. Right? It was not 8-bit addition. So we were getting wrong result. And then after this, we got the full 8-bit sum. Good? Yes? So any confusion around this? Any questions? I'm waiting for questions, okay? Take your time, reflect a bit, waiting now.
Ma'am, one
Yes?
proteus part.
Rimpi, I can't hear you properly. Can you please repeat?
Ma'am, once it open the proteus part.
Okay, hold on. Yes. Yes, tell me which part. Which part, Rimpi? Um, okay,
Ma'am, I just check with my simulation part.
simulation part. You can just type in your query again in chat box because your voice is actually breaking in between. I'm sorry. I'll just. I think you are explaining.
Ma'am, I have a doubt, ma'am.
Yes, tell me. Tell me.
Ma'am, when the carry is 1, ma'am, we are connecting C0 to C4. But if there is no carry, then what we will do to C0?
Okay. Okay, Soham, I'm replying you. Just let me address what Remy is asking me to do. Okay. So just here is the circuit, Remy. Remy, just take this. I'm playing the simulation, okay? Okay. Take yours with mine. Okay, thank you. Okay, so Soham, what you are saying is, uh, I think, let me confirm my understanding. You are saying that
when the carry is 1, we are connecting C4 to C0. But when the carry is not 1, then what we will do?
Okay, so that's you see, just it's like the sum, right? Just let's take a say case where the carry does not appear. Say let's make it very simple, like this. Say the first 4 bit. Okay, so the first 4 bit should be generating no carry. It's not generating any carry, so C4 will go 0. So there would be no carry input for the next 4 bit, right? So if I put as a simple circuit, a simple sum, say it is 1100, and let's make all of them as 0, and what will happen? A simple sum, say 0, 0, right? So that means what is happening? First 4 bit is not generating any carry. So no carry input here. No carry input. I'm showing you a PPT. So this C in would be 0. I said, right, it can be 0 or it can be 1. So no carry input here. It's like your decimal sum only. So you have no carry on this part. So only these 2 bits. Okay, these 2 bits will get added to 0 because both are 0. And if there were a carry, if a carry, say these 4 bits were like, say there was like this, say 1, and if you say 1, in that case, oh sorry, yes, that's not. Say it were like this, on the other hand, that will produce a carry here. It will produce a carry here, right? This is your, for the second stage, it will be the, for the second stage, this will be the carry output, carry input. In that case, 0, 0 and 1, these 3 bits will be summed up in the next stage, and 1 will be. So if it is not present, then it will be just 2 bits of sum, and if it is present, it will also sum up the carry. That is the like simple logic. So if you have already built the circuit, you can test it yourself, or you want me to do that? Because we have 2 more experiments. So yes, tell me.
You can perform one, sir.
Oh, you want me to perform once? Okay.
Yes,
Okay. Yeah. And Amrita is saying, ma'am, can you please explain the simulation part again? Okay. So which part you want me to explain? I mean, how I am playing the simulation? You understood how I built the circuit, right, Amrita? The input part? Okay. So let's, as I'll be also doing this particular simple sum for Soham, let's see if you can understand. Give me 2 minutes.
So I think the left part will be the answer summation part will be 1100. I think so. The left part.
Left part is, that means the higher order part is 1100, right? So Amrita, just put some focus here how we are making the circuit, okay? Okay, just let me write it down for you. Okay, I'm creating a space here to break the 2 stages, okay? And this higher order part, this 1100 part, will be performed by the circuit that is labeled as U2, and the lower order part will be simulated by the U1 adder. You can see clearly, right? U1, this is the label of this particular adder, and U2 is the label of the higher order stage we have considered. So this particular adder. Okay. Now let's make the inputs. Okay. So Amrita, if you do not agree with me, you should just unmute yourself and say yes or no something. Okay, I am making the circuit, put your focus. So this is U2, this is A, this is input A, and the first one is input A, and the second one is input B. So combinations get once again. Don't get confused. 4, 3, 2, 1. Again, for the lower order stage, 4, 3, 2, 1. Okay. So let's connect in this way. Okay. This is very simple. See. So for the higher order stage, let's connect this first. U2 will do this A1, A2, A3, and A4. So A3 and A4 are high because the bit values are 1. Excuse me. And A1 and A2 are zeros. So let's go and do that. Go and do that. I'm deleting all the wires. Whatever I had made, so it will be easy for you to understand. Okay. See, I'm not removing the cascading part. This is the only cascading part you can see from C4 to C0. That will be there. So only I'm changing the bit inputs, bit values for input. So as we saw that A4 and A3 are high. So let's connect them. Done. And let's see the other two bits we have to connect to ground, right? So this got to ground and this got to ground too. So we got the higher order 4 bits for A. Let's see the higher order 4 bits for B. All are 0. So all will be ground. Okay. So let's, this is the line coming from ground, right? So let's just connect them. Right. So all are 0 and this is 1, 1, 0. Correct? Okay. So this is over. The higher order 4 bits are over. And let's focus on these 4 bits, lower order 4 bits. And we see that all are 0, the first case, right? In the, so let's just delete this whereas. Yeah, I'm doing it yet once again for your clarity. Okay, just remove all the whereas. Okay, so let's see. All are 0, so 1. Correct? All are 0, 0, 0, 0. And then in part B, just the lowest bit, B1 is 1. So only the B1 is 1. Okay. Let's put all of them. And what should be C0? We have already discussed much, right? So for the lowest order bit, we do not have a carry input because we do not have a lower order stage. So definitely it will be 0. Correct? So this is our circuit. Yeah. I hope you can see. Let's play the simulation. Okay. So 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1. Some bits. And there is no carry. Okay. No carry output, so C4 bulb is not glowing. Cleaned. Amrita, is that clear now? Is that clear now?
Yes,
and
ma'am.
Soham? Yeah, Soham, you got your answer?
Yes, ma'am.
Yes? Okay. Let's see what Rimpi has sent. Okay, it's better. I don't know. Let's check it now itself. Okay. So the half of the things I cannot see, Rimpi. I only can see this lower order bits. But the simulation, yeah, it should look like that. But I need to see all the bits, right, to verify the sum. Or is it the same sum I had been doing? Okay. Okay, we'll see it a bit later. Let me just go through all of them because if I try to address simultaneously, a bit late. I don't.
Can you go to notepad once?
Yeah, sure.
Ma'am, in the U2 part, 0 plus 0 should be 0, not ma'am. Why it is given 1 there in the summation part then?
Yeah, it should be 0. I don't know why it can hold on. I think yeah, I think I was showing that with carry and that time it was like wrong. Yeah, it should be like this, right? 1100.
Yes, ma'am.
201. What was it? Oh yeah.
Yes, ma'am. It's coming there.
Yeah, that is correct. I did
Yes,
it.
ma'am. Okay, thanks.
Okay. So are we going to move to the next part? If you send it at your convenience, I'll check that. Don't worry. And okay, let's move to the next part. Yes, Rimpi, I got your message. I'll address that once my lecture is over. Don't worry. Okay, you must tell me that if this session is like feeling like overloaded or something, because I don't want you to overwhelm you. This is another circuit. This is, I think, more interesting because we will be implementing the subtractor using the same IC, the adder IC. Okay. Read the title. Implement 4-bit full subtractor using full adder IC and XOR gate. Okay. So I'll explain why XOR gate. You might guess as well. You might just think a bit. Let me first give you the basic theory. The theory is very simple. We need to implement subtraction operation using adder. Okay, so we are going to implement subtraction using adder. So how do we do that? This is a simple number theory, and what it does that if we know 2's complement thing, right? 2's complement. So we can think of a subtraction, say in decimal number. In decimal, say 15 minus 3 equals 12 can be thought of as 15 plus minus 3 equals 12, right? Now, when we are performing in binary, just imagine that these numbers have been converted to binary. So okay, let me write. The thing is just 1111, right? Plus this minus 3, I'm going to write in 2's complement form. So 3 in decimal, okay, I cannot subscript it, okay, never mind. Just 3 is in binary, um, 1, sorry, once a month, right? So this is the positive 3, and we can take the 2's complement to get a negative 1. And then how we calculate the 2's complement? We can perform the 1's complement, that is 1 1 0 0. Just we complement each of the bit 1 1 and then 0 0, correct? And then add 1, add 1. So how we get it? Uh, so what we get?
হবে না বন্ধ আছে
The
অনেক
2's
সাইট গুলো
complement,
শুধু বন্ধ আছে ওগুলো খুলবে না ওই জিনিস খোলো না যে জিনিস অ্যাভেলেবেল ছিল কিন্তু
plus 1 1 0, correct? So this is actually minus 3, right? Minus
না
minus 3 in 2's complement form, correct? And this is actually 1's complement. This is also minus 3, but 1's complement. So now you can see that the only challenge towards calculating this subtraction is we need to get this minus 3 in 2's complement format. And for getting the 2's complement, we need to get first the 1's complement, which is just the complement of each bit, and then simply add 1 to it. That's it. It's as simple as that. We need to implement this thing, what I like wrote in this summation form. We need to implement this operation in circuit. That's it. So how in circuit in hardware, how we are going to calculate this one's complement? How to do this in circuit? So we will be using in our experiment a XOR gate. So can you figure out how XOR gate can be useful in getting a complement of a bit? Is it possible? Yes, no? Any idea? Can XOR be implemented? Can complement of a bit be implemented using XOR? I think you have covered these two in your theory. This is also there in digital logic book. This is there in your CO also. So you should be able to answer it. I'm just repeating it for a recap. That's it. Can we complement a bit using XOR gate?
অ্যাপোলোতে ডেটাবেস পে পাওয়া যায় ওটা পড়ে আসলে কি দেখো এখন এসে
No prompt answer?
বলে ফোনকে জিজ্ঞেস করতে অসুবিধা নেই
Ma'am, if we take the another input like 1111, then
For what?
two input A and B, we have to find the complement of B.
Okay.
And our input and our input of A will be all ones. Then if we apply the XOR gate, I think maybe we can.
Okay, I'm writing what you're saying. Okay, so just tell me once again. You want two inputs A and B, and okay, and then give me the A input.
Any number one. Let's take 3 only. 0011.
0011. Okay.
And
so this is your positive number, right? A minus B.
Yes.
Yeah. Okay. And so the second one.
B, I will be using the second number B to find the complement of A. To find the ones complement of A. B will be all ones, 1111.
Okay. So you want to use Okay, you want to use B to find complement of A, right?
Yes, ma'am. And now if you apply XOR gate on A and B, I think
Yes.
we will get
Correct. So you want to use XOR gate. So yeah, I'm just repeating it. You're right. Okay. So I'm just explaining what you said to everyone. Okay. Yeah. So basically, what he said that we take two numbers and perform XORing. Okay. I'm just symbolically writing bitwise XOR. Okay. And we'll be performing a bitwise XOR on A and B. And what we will achieve, what we'll get is you know the XOR truth table, right? I'm repeating the XOR truth table. XOR truth table for A, B, and A XOR B, A XOR B. So 0, 0, 0, correct? Oh, yeah. What happens now when two bits are similar, then we get 0. When two bits are dissimilar, one is 0, one is 1, or 1 is 1, 1 is 0, like that, we get 1 in XOR logic. So 0, 1 would be 1, and 1, 0 would be 1, 1, 1 would be 0, right? So what is happening? Just focus on these two rows, okay? Forget about this uh, zero, zero. Yeah, sorry, I'm wrong. I wanted to tell these two rows. I cannot select or highlight. Okay, let me reorganize it. Okay, let's focus on where the B part is 1. Okay, just if you see that if I apply B as 1, it is basically complementing the A bit. That is what he said. Like, what's your name? So sorry. Yeah. So if I apply B bit as 1, then it is complementing the A bit, and the result we are getting is complement of A bit. It is always, I'm representing complement as the field. It is always the complement of the A bit. Correct? That is what he said. So if you take 0, 0, 1, 1, any number, it may be any number, and put all ones in the second operand, and then if you perform bitwise XOR, then you will find out that all the bits of A is getting complemented. That means in this way, we can conveniently get a ones. The only condition is that we have to put the second operand B as all ones. Clear?
Ma'am, can I explain once more, ma'am?
Okay, so I'm just see. You can see the truth table, right? This is the correct truth table, right? So for XOR.
Yes, ma'am.
Yes. So just focus on these two parts, these two rows. Okay? Yeah. So is this correct? Is my conclusion correct? That if B is 1, then in the result is or B will get the complement of A. So let me write in English, okay? If B is 1, then A XOR B, this is bitwise XOR operation, is going to give me A complement. Is it correct? Yes, so I'm convinced?
Yes, ma'am.
Yeah. So look at any number, okay? So we will perform this bitwise XOR. Actually, if I give this A and B, now it is confusing. This is altogether different operation we are doing. We are performing here A1, say XOR B1, where
Yes, sir.
this is bitwise XOR. Okay, so this is what we are performing, and this is the result. So if A1 is a number we want to complement, then with the second operand, we can apply all ones and then perform a XOR operation. Okay?
Yes, sir.
Yes. So in that case, it will calculate the ones complement of A. Understood? So what is happening here for one single bit of A, this is happening for 4 bits, 4 individual bits of A. Because we are performing the XOR bitwise. Okay, this is not a sum.
Yes, sir.
This is a bitwise XOR. Take one bit at a time. Just take and cancel. Okay, logic of it. So this is what is happening.
Okay, ma'am.
Okay, thank you. So I think you're clear. Okay, let me save it. Okay. So can we implement now? So we have got, okay, this is not complete yet. We have to get a two's complement as well, right? So this is one's complement. We want to get two's complement, correct? So in two's complement, what we have to do? So add 1 to the one's complement of A. Sorry, not this A and B is confusing. Due to this example only, rename them all. Never mind. This is a logic operation, and that part is over. And going back to where we left the discussion here, right? So we will be performing one's complement of B. Okay, perform one's complement of B by how? Now perform bitwise XOR for B. Okay, bitwise XOR operation with and for this XOR we have an IC that is in this experiment I'm going to show you the XOR IC. Just we cannot simulate that IC actually. That is problem, but I'll show you the pin diagram. That's very simple, very simple. So for XOR, you will see an IC 74 series 7486. Okay. Let's let's calculate next. This is step 1, and to get the second two's complement, we need to just add 1, right? So here in the second step, perform just addition, right? Add 1 to the one's complement of B from from step. Is this clear to everyone? And how we are going to perform this add 1? We'll see. Okay. We'll see. So what is happening? Let me write it like this. So I'm taking this particular example only, okay? Repeating it here. Using decimal, I'm going to write. So A is 1111, and then B is your. How we are going to do it? It's 0011 bitwise XOR with uh, 4 bits, so 4 bit, and then we have a carry input, right? We have a C0, and in C0 I'm going to put 1. Okay? And then what it will give me, I'm going to add all these 3 numbers. Okay, it's going to perform all these 3 numbers, and what we are going to get is just right, and is 1 complement, right? 1 1 0 0. So these 3 numbers will be added by a full adder, 4-bit full adder, and what it will get is, okay, let me see, 110 and 1 carry, then 110, 1 carry, 1 carry, then that is 3 1, so we get 1 and 1 carry. Yet again 3 1s, so 1 and 1 carry. So we have this. So we have this output. One, right? We have this output 1 carry, and this is your, in decimal what we get. When we perform whose complement like this, this is the C out, okay? So C out we get 1, and sum we get 12 in decimal, right? 8 plus 4, 12 in decimal. And when we perform such a subtraction with two's complement form, then we can ignore this particular carry that is coming out in the result. Okay? So we will ignore the keyboard, okay? Carry out keyboard on this sum. Okay? Is this logic clear? I hope this logic is clear at least. And we will quickly see the circuit. I need to, let me show the circuit, okay? Because it will take some time, and I have got only 15 minutes left, I guess. So I think I have already made this. Okay. So you can see here what is happening here. So this is a full adder 4-bit, and then you see this A input is like what we did earlier. Simple, simply connected to 1 1 1 1. This is the same example, okay? 1 1 1 1. All are connected to the high port. And the second input, that B input, each are performing this bitwise XOR. Okay. So if we want to pick part, so what part we are using is, I will show you. 7486. You should search for the XOR gate like this. 7486. 7486. Okay. And then go for this instance. Okay. Go for this instance in Proteus. This is all the things I'm showing. This is for Proteus simulation only. For hardware, actual implementation, the circuit and not the circuit, sorry, the components may be different. Okay, that is whatever is available in lab that will be using. But in Proteus, this is the active component 74LS86 that we can simulate. So make a note of it, okay? Make a note of it. This particular component. Few of the components here cannot be simulated. Okay. Okay. So I'm moving forward, right? So what we are doing, let's focus on the circuit. So you have the XOR gate, 4 XOR gates, because there are 4 bits, and we are performing bitwise XOR, means 1 bit at a time, right? So in that case, this one operand is B. So whatever the input of B, that will be providing in one pin of this XOR gate, and on the other input will be providing the one, simply one. So let me show you one case. One case. So when I disconnected, oh yeah. Let me show you one instance. Okay, say this is the lower order bit A, B, C, D. Okay, this is connected to B1. So B1 is here basically in circuit. In the circuit, pin B1 would be connected to the complement. Okay, that means this complement which is obtained from B XOR 1. That means the output of the XOR. So the B1, pin B1, B2, B3. This is true for all the 4 cases. This is true for all the 4 cases. Pin B2 will be at, say I'm naming it XOR gate output 1, say it is Y1, and then for B2 will be connected to XOR gate output 2, XOR gate output say 2, Y2. Okay? In the same way, the rest is done. Okay, fill in the blank. B3 and B4. The rest is done. So let's just take it for this circuit. What we have here, let's look at B. What is B? Is 3, right? So here the lowest bit is 1.
Perfect.
Please mute yourself, or Nabrato. You are unmuted. Okay. So this is the lower bit. Lower bit is 1. Okay. And then it will be put. So let's see. Say the pin 1 is say pin 2. Pin 2 is okay. You see that this is the power. This line is coming from power. So I'm putting 1, and this A, this is also 1, right? 1 1. So one, this one pin, the pin 1, we are giving input for B, and for pin 2 we are giving 1. So let me just label it. Maybe we have a label. This is label I'm using. Okay, so here say the input is simple 1, and this is. this is the value of B. We will actually put. Don't get confused. Okay, this is the input value, the lower order B, and we perform the XOR, and then the output here. I think we don't have the output here is complement, one's complement of B1. Okay, that is the output of XOR as well. So let's mark it as XOR. So this is what is happening. Okay, so this second pin I am putting B original input, okay, non-negated original input in pin 2, and in pin 1 it is connected to, you can see all the circuits, it is connected to 1, should be connected to 1. Okay. There is, I think this is a power source as well. So you can see this second, the first pin is always connected to VCC, and the second pin is connected to the original input B1. So there is no such need that it is always has to be like this, like first pin should always be 1 or 2. So you can, like, it is what you wish, as you wish. Okay, you can just make sure that one of the pin of the XOR gate should be 1 always, and another pin should be the original input of B1. Okay, so then the output will be connected to the IC B1, B2, B3, B4. So this gives me the complement of B as the input to the IC. And then T0, here is the carry input, right? This should be set as 1, right? This is the power line, so it is set as 1. Okay, and this circuit is implemented for this 15 minus 3, what I showed you here. And if I simulate it, okay, I said like we'll ignore this carry. There is no meaning for this. We'll ignore this. So only some bits, if you see 1100, okay, 1100, that is 12 decimal. So that is correct output, right? So tell me, is there any confusion? Because I think the time is over. And yeah, if you have some problem in this part, like for the subtractor part, we may just review it in the next lab class, because there is another extension to this, small extension that will not take much time, and or I'll include in today's assignment itself if you're comfortable. So just give me your confirmation that if I should include it in today's assignment or what. Because I don't think it is much complicated, but you should try it once to be clear about it. Let's just think a bit. And time is also over.
I hope that all of them have given the attendance, right? The link was posted there in the chat box.
Yes,
okay. Okay, we can end the session. It's already 11:29.
So I just wanted to know whether we should include it. We can include it in today's assignment. Actually, you can try it in your home. Okay, I think there is not a problem if you cannot, like, do it, then skip the question, but do the other two questions. Don't like be worried about marks or anything, but you can include the solution in the next class maybe. So I'll keep it, okay, the subtractor part only, and try it at your home and see if it works for you, okay. And if it works for you, then you can include it in your assignment, okay.
Ma'am,
And
when will we have to submit the assignment of today?
okay, see, you can see that in the PPT I have given. It's 13th, 7 p.m. I hope the deadline is not too close.
Ma'am, where will we have to submit it?
I will provide you a link. You have to submit it in